Hey everyone, today I'll be talking about this paper, Directed Policy Gradients for Safe Reinforcement Learning with Human Advice. This paper is by Helene Plisnier, Denis Steckelmacher, Brys, Diederik Roijers, and Nowe. Now, although this is a workshop paper, I've picked this up because of a couple of reasons. First being the simplicity of the idea, followed by a really good discussion section both in evaluation as well as introduction. So let's begin with it. Now let's look at the title itself and break it down and understand what this paper is hopefully trying to achieve. So first of all, it says directed policy gradient. So definitely it would have something to do with policy gradients. Well, policy gradient is a type of technique that you use to get a good policy in scenarios where you're using reinforcement learning. And one of the things that you want to do is perform something known as safe reinforcement learning using human advice. So there are different components here, and we may not get all the components as we go along in this paper, but anyways, the bigger idea that this paper is trying to go for is, well, there is a method known as policy gradient. What we want to do is incorporate human advice in the hope that the ultimate agent that we get, that is the policy of the agent that we're getting, is safe by some metric. The paper's motivation is pretty straightforward, that human advice has been used in a plethora of techniques given here, but of course it hasn't been used with policy gradients, and a direct manipulation of policy gradient has been found to be difficult, and now these people are trying to go for a simple solution towards that. They give a general background on MTPs and what a policy gradient is. We can delve into that in the later part of the video. So their basic idea is something known as mixing policies. Of course, this is not their idea, but they are trying to generalize from a previous work by Griffith in 2013. And they say that you can extend that idea for something that they are doing. Now the solution is like a pretty straightforward solution. We can discuss it in a minute maybe. So let's say that pi L is the policy obtained using some policy gradient method. You get this pi L using that method. And let's say pi H is a policy given by the human. So note that in this paper, the term advice is being interpreted as the fact that somehow, directly or indirectly, before using this method, you have access to pi H, which is the policy that a human would give as an advice. Now, this policy could be stochastic or deterministic, and they support both of those kinds, and they have a good discussion about what happens in either of those two cases. So again, the requirements are that you have a pi L, which is the policy given by the policy gradient method, and you have access to pi H, which is the policy of the human, right? What they believe was supposed to be done. Now, following on the work of Griffith, the authors in this paper, they say that, well, why not just combine these two policies by, let's say, a new function pi, and the way we combine them is given here in this equation 2. So the pi H given by human basically says if you are at state S2, you take action A2, and the tuple looks like S2 equals 0, 1, where it's 0 probability you're choosing action A1, and with 1 probability you're choosing action A2. Now if you look at the Q-learning case, first of all, here given by, well, not this, but these 3 lines, you will directly see that there is no way, or there is no place at least, where Q-learning is incorporating this advice, because you can't force Q-learning to do it. At least this is the baseline that the authors are going with here, that Q-learning has been adapted directly. Now how Q-learning works is you take the current reward and the temporal difference, right? So what we need to know is that there is a presence of this max operator. What it says is if you are in state S2, right, rather than picking or forcing Q-learning to choose a specific action, you will just take the max of what you were given, right? So you'll just directly choose A1, which is what they do here. If you're at S1 and you pick action A2, the subsequent reward is at best plus 10. Now let's focus our thing on the second baseline that they have, which is SARSA. Now SARSA has a different update rule, because of which you don't have a max operator in the equation, right? Hence, you can actually surgically change the output. So here, instead of using Q of S2A1, we'll pick Q of S2A2 because that's our action that we'll choose, right? Because here, this is actually in theory pi of S2, right? Which is A2 in our case. But this is an off policy method, and at least they have not chosen a Q-learning based advice taker. Finally, I found discussions on policy gradient, which is supposed to be the thing that the authors are dealing with, to be slightly vague, in the sense that these discussions are pretty short and straightforward. I'm not sure if that's a bad thing, but they really talk about that since policy gradient is going to converge, it will converge on the right thing, which is this, and we'll directly use our pi function, which is pi L and pi H, a function of pi L and pi H, and it will yield us the best anyways, right? Regardless of the kind of advice that you've given, whether it is a correct advice or an incorrect advice. A similar discussion happens in the case of stochastic advice, right? Where they're criticizing the SARSA algorithm as well. The criticism is with respect to the fact that SARSA typically uses some exploration strategy. One such strategy that they've shown here is epsilon greedy, where with epsilon probability you will take a certain action, and with 1 minus epsilon you won't take it, or vice versa. You can just name it around. Now, because of this epsilon, the way that they have merged the two policies pi h and pi l here leaves this epsilon term in the end of pi. Like while sampling, you still have this epsilon term there, right? So even though, let's say in this case, the first action was better, right? A1 is better than A2. We won't choose A1 every time. Remember, we are sampling here, and because of this epsilon, it is not a 1-0 tuple, right? It will be 0.999, and the A2 action would have some other value, right? So we can't necessarily force the agent to choose a certain action because we are always sampling. And they have criticized basically this point that you are sampling. On the other hand, in policy gradient, they say that, well, we won't need to sample because it would converge to a deterministic solution. But on this note, I think a straightforward way would be just to determinize this by using some threshold, and maybe that would work for most of the times, and using SARSA is not such a bad thing. Finally, with respect to evaluations, they compare with their own strategy with reward shaping. So in this first case, you're using action advice. So you've been given a policy and you're trying to incorporate that policy into the agent's policy. And in the second case, it's a more indirect thing wherein you've been given rewards instead of a policy, and you use those rewards in order to induce a better policy or induce it faster for this agent. Now, although they have given other reasons in this discussion as to why policy gradient would be better, I think a straightforward answer should be the fact that the assumptions used in this paper are much stronger than the assumptions used in the reward shaping works, right? Because here in this work, we have directly assumed the presence of a pi h function which maps states to actions. This is a much stronger thing to assume rather than saying, oh well, I just have access to rewards for this state, which in turn will give me what a good action is. Now, I think the presence of more information in this work directly answers why it would be better. But the thing that this paper lacks is, why is it easier to assume that we might have this pi h instead of a reward shaping function? The other thing which is pretty interesting, and I encourage more works to follow, is this idea about comparing what happens when in an iterative learning fashion the advice is stopped midway, right? So what they have done is, let's say there are two trials. First is the human would be involved for some X length of time, and they'll leave probably and won't advise the agent anymore. And in the second case, the human will just keep on advising for a long time. So what happens in these two cases, and how does DPG performs? So finally, I think this was an interesting work, but the other criticism that I have is, nowhere in this video at least you would have heard me saying the word safe, and neither did the authors say it in their paper, right? So a discussion on why are they concentrating on safe reinforcement learning is missing, and I think what the authors are trying to imply is the fact that we can incorporate human advice. It will work mostly for safe reinforcement learning scenarios, but I don't know if that's true, because their environment was pretty straightforward, the one that they've used in this paper, and that did not have any concerns with respect to the safety to the agent or to the human or to any other entity. So I think this could very well be improved if they have a discussion on the safety of things. The other criticism I have is with respect to this deal about policy gradients converging to the optimal policy, regardless of the kind of advice given. So section 4 makes it a big deal about what happens if a phony advice is given. Now I think as a community there should be a discussion with respect to the interpretation of advice. In this paper, this advice was more of an instruction that if it has been given, you must follow it. And so an incorrect advice can really hurt the agent, and policy gradient methods will go out of their way and not follow an instruction. So I'm not sure whether that's a good idea, because if it's an instruction, then maybe the human knows more than the environment reward designer, and the agent should in fact follow the human's advice. Finally, my last concern about this paper was, here in the conclusion they say, we show that DPG allows good policies to be learned from scarce advice. I'm not sure if it's scarce advice, because they have ultimately assumed the whole policy to be given to the agent by the human, which is a big function to give, right? For all the states you have to provide what happens if I take, or with what probability should I take an action, which is a pretty big function, a pretty big data that you have to provide. Now, unless the paper were to make a big argument about how easily you can learn PyEdge and then subsequently use this work, then I would concede and agree that that would be an interesting thing to incorporate. But I don't think this was highlighted enough in this paper. Finally, as some good pointers about this work, I think this was a pretty simple and straightforward approach, and it was pretty clear in terms of reading. The experiments were straightforward, to the point, and I understand they might have some issues in them, but they were pretty direct and easy to understand. So I encourage people to read this paper and comment about what they think, how it relates to their research, and if they can incorporate it directly into the things that they are doing. So thank you so much for watching this, and I hope this review helped you with this paper.